This is the solution video of question 3 of the module's Mohr circle of 2D stress and strain transformation. In this question, the state of strain at the point on the bracket has the components as following. For the first part, part A, use the strain transformation equation to determine the equivalent in-plane strains on an element at an angle of 30 degrees clockwise from the original position. Part B, sketch the deformation element due to these strains with the XY plane. And for part C, use the Mohr circle to solve the problem again. So first of all, let's look at our strain transformation equations, which are as following. To save us a little bit of time, I've just left them as such, and you guys have these notes available on Canvas in case you want to access them afterwards. These equations were also presented in your lecture. So the first part that we want to do, we want to write out the equation for the transformed X, Y, and normal strain and our shear strain. So for our transformed strain in X, simply using what we have been given, which is 400 plus minus 250 divided by 2 plus 400 minus 250 divided by 2 cos 2 times our transformation angle, so that was given as 30 in this case, plus our shear strain 310 divided by 2 sine 2 times the transformation angle. What we'll find is that our strain, or our transformed strain in the X direction, is 103, and please don't forget that is times 10 to the minus 6. So I just left that out in this equation. Let me just add that in. I did run out of space, so I'm just going to make this equation a little bit smaller so we can fit that in on our page. There we go. Times 10 to the negative 6. And then we're going to go ahead and look at our strain transformation in the Y direction. And similar to when we calculate our stress transformation, these equations are pretty much identical. So I'm just going to copy this one, paste it in here. What is the difference though? It's simply just that these parts in here, it's going to remove them, where we had our plus sign. Okay, and I'll do that in blue so you guys see where I'm doing this. So negative, just like in the strain transformation equation here, if we look at the difference between the X and the Y, it's simply just the signage in there. If we put that in our calculators, we will find that our transformed strain in the Y component is 46.7 times 10 to the negative 6. Then we're going to go and look at our shear strain transformation. So again, this is our shear strain. Simple just, and again, I'm going to transform that and divide it by 2. I'm just going to put that on this side, so times 2 my 400 minus 250 divided by 2 plus sine, sine 2 times the transformation of 30 plus my shear strain 310 divided by 2 cos 2 times the transformation of 30, and there we have it. We put that in our calculators and we get 718 times 10 to the negative 6. Because we already have our angle, and I believe it even states, so let's go back. In the question, it states that our angle is 30 degrees clockwise, right? Which means it's rotating this direction. So we have our x in here. So this is our element. They've given it to us. Our x in the question, the transformed element would then be transformed clockwise, which is this direction, and this would be our x dash. So let's just sketch that up just below here. We'll find that our original y is this direction, just out of standard coordinate fields. Original x, our transformed element, something like this, right? And 90 degrees away from our y-axis is our y transformed. Always 90 degrees away from each other. So it's just tilting the original one. And what we can do, we can put our strain element. So we have the original element, this then refers to our strain in the y. Transform strain, and then the transform strain in the x. So then our transformed angle usually refers to the angle between our new transformed axis. I'll just put it out here just because it's a bit clearer. And our transformed angle was, in this occasion, it was given to us as 30 degrees. So from the original plane to the transformed plane. And if we recall, it was given as kind of clockwise, hence we tilted this direction. Right, so for the last part, we are going to go ahead and solve this question using Mohr's circle. So this was our section B to draw out the element. Section C, we're going to do the same thing using Mohr's circle. Similar to when we did our stress calculation for Mohr's circle, we're going to still use the CR squared method, where C is our step 1, which is our center point, which is basically our average strain in this case. So C equals to average strain, which is just our strain in the X plus the strain in the Y divided by 2. So recall the stress, it was the stress in X and stress in Y, pretty much the same. So 400 plus minus 250 divided by 2. So all these values are 10 to the power of negative 6. Just to save me a bit of work, I'll put that on the outside. So 75 times 10 to the negative 6. Step 2. We are going to find our reference point, A. Again, just as our stress calculation, pretty much the same. The only difference is, we will see that shortly, so strain in X. But when we have our shear, so in this case shear strain, it's always divided by 2. That's the only difference when we do Mohr's circle between stress and strain calculations or drawings, whatever you want to call it. So A is in this occasion 400 and then 155. We had a shear strain of 310. All I did was divide it by 2. And I'm going to add my 10 to the negative 6 on the outside, just to save some room. Step 3, my last R, talking about the radius. Right? And my radius in this case is simply just the square root of my strain in the X minus my average strain squared plus my shear strain squared. So let's input our values. Square root out of 400 minus 75 equal to plus 155. Just recall, sorry, I missed this part, but divided by 2 again. Just remember, all the shear strains are divided by 2. So that's why I'm using the 155 squared. Put that in our calculators. What we'll find is that our radius is 360, again, times 10 to the negative 6. So perhaps I'll just put that slightly, the negative 6. Up to you how you want to indicate it, but as long as you keep track on your 10 to the negative 6, it's all good. Now I'm simply just going to draw my circle, since I already know where my center point is. Again, if you are drawing on a piece of paper, draw your horizontal first, and then your circle. So you have your center point on the horizontal. But because I'm doing this on my computer, it's simply just easier for me to draw the circle first to get the right location. Horizontal cuts half through the circle. Ideally somewhat correct. There we go. The positive axis to my right hand side for the normal, positive direction to the right hand side for my normal strain. My shear strain will still remain on the vertical axis, but first let's locate our center point in here. This is my center, C. I can then go ahead and draw my vertical point, right, which is located slightly to the left-hand side of my center point, probably somewhere around here. I then know that I then know that my principal strain 2, which is the same as my minimum strain, is located on the left-hand side. And then my maximum principal strain 1, is located on the right-hand side. It's positive. Again, this can exist on the negative coordinate field. It all depends on your center point and your radius. Then we want to go ahead and put in our reference point A on this coordinate field. So our reference point A is positive 400. So first of all, positive on the normal strain axis to the right, so towards my equelent 1, and downwards as positive for my shear, so 400 and 155. So let's put my reference point A at this point here. So A, 400, 155, also same as A, shear strain xy divided by 2. Don't forget to divide it by 2. And what I want to do, I want to draw out all my relationships. So center to my A. We simply know that this is going to be my radius, right? And then I want to go ahead and find my transformed strain, which is, I know it's going to be located 30 degrees from my original X plane, right? So recall from previously, along this reference point A, if I think about my element in the normal coordinate field, this is my X, where my angle simply is 0. But what we know now is that we have a transformed strain, which is going along, or which has an additional 30 degrees. So I'm going to go ahead and add my A dash, which I believe is going to be somewhere down here. That's better. And at A dash, let me connect the dots. Again, still going to be located radius away from the center point, but this point is now my transformed strain, where my angle, so the angle within the element, I'm going to call them the same thing, but within the element is now 30 degrees. If we go ahead and find our transformed element, we will start by finding the angle between our principal strains. So my 2 theta P1. I'm just going to call this one the additional 2 theta. Might be slightly confusing, but this one is P1, this one is just theta. So the complete angle alpha, which now is the element angle, I'm going to go ahead and find my alpha. Simply just angle between the principal strain and our reference point. So 2 theta P1 plus the angle that we were given, so 2 theta. I don't know this theta P1, so before we can figure that out, if we just go ahead and look at the graphical intersection between our reference point and Mohr circle, what we'll find from our reference point just all the way up to the normal strain axis, we will have this dimension in there as our shear strain divided by 2, which we have written down here. It's just 155. But we also need an additional few dimensions, and I'm going to include them in here, which is this dimension here between the center point and our reference point. We don't necessarily know that just yet. So how can we figure that out? Well, we know the distance between the reference point and the axis out here. So that's our 400. But we also know the distance between the center of the circle and the shear axis, which is just the shear strain average. So if we want to go ahead and find this section here first, 2 theta P1 equals to 10 to the negative 1 shear strain divided by 2 minus the normal strain in X minus the average strain. What we'll find is that 2 theta P1 equals to 25.5 degrees. If we then use this up here, we'll find that our alpha equals to 25.5 plus 2 times 30 degrees, right? That has already been given, and our theta P1, that's what we just found down here. Our alpha is then 85.5 degrees. If we then go ahead and find the transformed strain in X, again, this can be solved from the Mohr circle. So in here, so we're talking about the transformed one, which is this A dash, right? And we're talking about the X-axis. Let me use this green color. The X-axis we're talking about is now referring to this green one up here. So vertical cross. So we're talking about that distance up here. And we are talking about the vertical distance, again, following this green one. Just going to crop that out. We have a bit of writing in between, right? So hopefully that's not too confusing. this is just referring to our y dash. I'm going to call this x dash. Okay, so again, just these dimensions, we have this angle, so we're basically just looking at this green triangle, referring to the A dash. Don't want to fill that in too much, just so you are able to read those notes in there. Okay, so our strain in the transformed x-plane is simply just our strain average plus our radius plus our new angle, which we just found, so 85.5 degrees, 4 times 10 to the minus 6. So if we put the values in there, so we have 75 as our average strain, plus the 360.1 for the radius, plus our angle from the normal strain axis to the transformed plane, which is simply 103 times 10 to the negative 6. And again, we're going to do the same for the y direction of strain, for the transformed strain in the y direction. So again, simply just our average strain minus the radius plus the angle that we found between the principal strain axis and the transformed axis. So the 5.5 and 10 to negative 6. Again, put the values in, it's just the same as above, just negative instead of positive. 360.1 of negative 5. 5 which will give us 46.7 times 10 to the negative 6. And our maximum in-plane shear strain and our transformed strain is simply just our R sine the transformation angle, the complete angle, which is just 360.1 times 10 to the negative 6 sine 85.5 degrees, which is 358.99 10 to the negative 6. If we just want to find the transformed shear strain by itself, we simply just have to times this value by 2. So we'll find that it's 780 approximately times 10 to the negative 6. And that completes this question.